Hi everybody. Today we're going to move on into talking about continuous probability distributions. The most common one we're going to be talking about is called the normal distribution. So in Chapter 5 we discussed probability distributions, specifically discrete probability distributions, which are when you have a finite number of values that, or a countable number of values that your variable can assume, like for example the one with the number of heads you get when you flip a coin, where it was 0, 1, 2, and 3. And that was discrete because there are gaps in between those values. So now we're going to start talking about continuous probability distributions. And the big one we're going to talk about is this one called the normal distribution. That's a really common one studied in statistics. So to preface the normal distribution, first you can imagine a discrete probability distribution with several categories, and each of those categories having some probability associated with it. So if you look at this first graph over here on page 84, you'll see there's this middle column here, this middle bar, which is some class, and it has a probability associated with it of 0.3. So that means 30% of the data fall in that class. And then you can see, and that's probably somewhere around where the mean is. Still trying to get the hang of this whole thing. So that's probably somewhere around where the mean is. And then if you look to the left of that class and to the right of that class, you have these two more groups, which are both a little bit smaller. They both hold 25% of the data. And then as you go even further away from the mean, towards over here, and over here, you see there's 10% of the data in each of those classes. So the big idea here is that as you go further and further away from the mean, you get fewer and fewer data there. Okay? And this is just one breakdown if you broke down all of your data and grouped it into 5 classes. So if you look at the next diagram down here, it kind of looks similar. And what we did is instead of having 5 classes, like in the first graph, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. So we've chopped all of our data up into more classes, which means that we have kind of less data inside each individual class, but the relative frequencies kind of stay the same. You see, as you go, this is probably where the mean would be, right around here. And as you go further and further away from the mean, you find less and less values. Okay? And then this third example, you see it broken down even finer. And you can really start to see that this thing, as you break it down finer and finer, it doesn't look so much like a step, like steps like that first graph did, but it looks kind of more like a curve, doesn't it? Yeah, it does. And also, if you add up all the probabilities, I forgot to mention this, if you add up all the probabilities in each graph from the first 2 examples, they all add up to 1, just like our probability distributions did in Chapter 5. And we can't fit all these numbers inside of these tiny little rectangular things, but if you did, they would all add up to 1 also. And so, if you imagine theoretically breaking down these rectangles into smaller and smaller and smaller widths all the way to infinity, you get what's called what is like a continuum, and you get this nice smooth curve right here, and with a total area under it equal to 1. And that total area of 1 being what you get from adding up all the probabilities. We said before, if you add up all the probabilities in either one of these, you get 1, and the same thing is true here. Okay? And we call this a probability density curve, and these are the kinds of things we're going to be studying as we study these continuously distributed variables. Okay? Cool. So, section 6.1. Section 6.1 talks about continuous random variables, and specifically the one I just talked about called the standard normal distribution. So a couple things that's true about, we have some definitions and some facts here. I'll highlight the important ones here. In a probability density curve, the total area under the curve must equal 1. That's something we just talked about. And the second thing is that every point on the curve must have a y value greater than or equal to 0. That basically just means at any specific value of the variable, there's a probability of it occurring greater than 0, which I think should make a lot of sense if you think about it. Okay, we have something here called a uniform distribution. We don't really need to talk about that. We really want to talk here about the normal distribution, though. The normal distribution has a probability density curve that is symmetric and bell-shaped. Okay, just like those examples we studied earlier, where basically if you look at the mean of a normal distribution, you have a lot of values here. And then as you go further and further away from the mean, you find fewer and fewer and fewer values here. Okay, now this curve right here has an equation for it. And that equation is right here in this box. This f of x equals e to the negative 1/2 times x minus mu over sigma all squared all over sigma times root 2 pi. So take that down. You're going to want to memorize that formula. Just kidding. We're not going to be using that formula at all. We will be using software, computer software and calculator software to help us analyze that curve for certain values, which is pretty cool. And it's pretty nice that we can do that now. Okay, so in this formula, right, so this is one example of a curve right here. The key is that a curve is always centered at the mean, and it will always have some standard deviation sigma. So depending on what the mean is for that data set, we'll obviously shift the curve to the left or right, depending on whether that mean is, high or low. And the standard deviation, depending on whether the standard deviation is high or low, will kind of stretch out that data set. If it has a high standard deviation, kind of like this picture right here, or it'll shrink the curve if it has a small standard deviation. Okay, and that some of that information is described right here. Something to keep in mind is that the total area under the curve is always going to be 1. Okay, so what we do is we condense all of these different distributions. We have this curve, we have this curve, we have this curve. We have tons of different curves you can make for every single variable, depending on what its mean and standard deviation is, and we condense them all down into one curve, and we call that the standard normal distribution. So what we do there is we let the mean equal 0 and sigma equal 1. Okay, so basically what kind of data set will the mean equal 0? I'm sorry, that didn't really make sense. The way we can rearrange these values in some sort of way to make the mean equal 0 is to transform our variable into its z-scores. So we're going to transform all the values of our variable into their z-scores. So for instance, if you have a score that is equal to the mean, it's going to have a z-score of 0. Okay, so the mean will have a z-score of 0. So we're going to let that value have a value of 0. Okay, and the standard deviation is going to be 1, which is also going to kind of represent z-scores. Okay. All right, let's keep moving along. So, in the back of your textbook, you have a table that's really helpful with these standard normal distributions. And it basically does something that, remember that formula that I said you don't have to memorize? It calculates a lot of values under that curve and calculates them for specific z-scores. And this table is sometimes referred to as the z-table. Alright, so let's do an example together to see how this works. So the first example is find p of z less than 1.35. Alright, so we're trying to find the probability of some z-score being less than 1.35. So here you have our normal distribution curve. And so the question is asking if I wanted to analyze a z-score of 1.35 in a normally distributed data set, Here's my z equals 1.35 above my mean of z equals 0. What would be the probability of picking some random data value that has a z-score less than 1.35? And so you see here's your normal distribution. So what we're trying to find is the probability of this whole region to the left of our z-score. And one way we can calculate that is to calculate the area underneath this curve right here, this little section. Oops. This little section here. Sorry, I'm very not good with this. Okay, and the way we do that is we're not going to do any calculating at all. We're just going to look up a value in the table in the back of the textbook. So see pages 288 and 289 give these probabilities. So if you go to page 288, okay, these are your negative z values, okay, and you can see this table right up here. Right here, you see the z is to the left of 0, which means this would be a negative z-score over here. Okay, and if you go to the next page, on page 289, you'll see this little diagram over here. You'll see this z-score is to the right of 0, which means it's a positive z-score. Okay, so this for this example, we're looking for z, the probability of z being greater than I think it was 1.35. So we're going to look, or I'm sorry, I think it was less than 1.35. It is less than 1.35. So this table, what it does is, see how this highlighted is all less than our z-score? So this table right here shows us the probability of exactly what we're looking for, getting a z-score less than 1.35. So what we need to do is look up this value in our table, and you'll see this column right here is all z-scores to the ones place and the tenths place. And then this row over here is all the hundredths places for a z-score. So you need to use both of these to find some z-score with 2 decimal places. So for example, this is 1.35. So we're going to go to z equals 1.3, which is right here. And then for the 5, we're going to go up top and look at the 5, and that's the hundredths place. So right here is our 5. And we're going to see where those two columns meet. So 1.30, 1, 2, 3, 4, 5. And this is the value. So basically what the table tells us is that there's a probability of 0.9115 of randomly selecting a value with a z-score less than 1.35 in a normally distributed data set. Okay. All right, cool. So that was that first example. And you'll see a couple notes here. I wouldn't worry about this first note here so much, but this second note is really worth exploring, and that is the probability of getting a z greater than 1.35 equals 1 minus 0.9115, which is 0.885. Why is that the case? So this area right here has a probability of 0.9115. Why does this area here equal 1 minus 0.9115? Why is that the case? Well, if you recall the fact we said about normal distributions and probability density functions earlier is that the total area underneath this curve is always equal to 1. So if we already know this one, this side, the left side of this curve, then the right side is just going to be 1 minus that. And then once you get that result of 0.0885, then you can verify that these two things both add up to 1. Okay, cool. Let's do the second example. Find the probability that z is less than negative 1.35. So again, you want to identify z negative 1.35, which is going to be to the left of 0, right? I always like to draw my curves. Even though the textbook has them drawn, I like to draw them myself. So we know that's to the left of 0. So we know that is going to be in the first page of those tables under the negative z values. And then we just look it up in the table. Z equals negative 1.35. If you go down your z column, you get negative 1.3. Then you're going to go over to the 5, 0, 1, 2, 3, 4, 5. And there you have it, 0.0885. Okay, and you'll notice this first note right here says, notice that probability of z being less than negative 1.35, what we just found, is the same as what we found later in the previous example, the probability of z being greater, oops, see if I can draw this, no, this area right here, which is the probability of z being greater than positive 1.35. Why are these two things equal? Why is this equal to this? Well, it has to do with the fact that the curve is symmetric, and that's exactly why. Okay? And another little note here. The probability of z being less than 0 equals 0.5. If you look that up in the table, if you look up 0.0, you'll find the answer is 0.5. Why is that the case? Think about that. Well, z equals 0 is the middle of this distribution. And like we just said, it's a symmetrical distribution, so you'd expect half the data to be below 0 and half the data to be above 0. So that's exactly why. Okay. So what we can do is we can actually generalize this procedure, I guess you could call it, that we just did in the first example. And that is to find the area to the right of a z-score. So to be clear, to find the area to the left of a z-score, I'll type this out here. Whoops. Okay, I'm not going to type this out here. To find the area to the left of a z-score, all you do is look up that value in the table. Now to find the area to the right of a z-score, you just, whatever value you're looking for, so say if you're trying to find z is greater than some z-score, which is what this kind of confusing notation right over here represents, you just find that, you look up the value in the table and you subtract it from 1. Okay? So let's go on to example 1 and do these together. So example 1, find the requested probabilities and shade the appropriate region under the curve. So for this first one, we have find the probability that z is less than 2.58. So what you want to do is go to 2.58, positive 2.58, and we're trying to find the probability of z being to the left of that number. So we want to go to our table in the back. We're going to go to our positive z tables, right? Okay, here's our positive z tables. We're going to look up 2.58. So here's 2.5 down here. Now I got to go all the way over to 8, which is right over here. So 0.9951 would be the answer. Okay, and that's where they got this 0.9951 answer from. Okay, now what about P of z being greater than 2.58? Well, greater than 2.58 would just be kind of the z-scores in the same place. Now we're just trying to find the other side of it. So since we know the total area under this curve must equal 1, then that means the answer for this is just going to be 1 minus the area to the left of it, which we already found. And if we didn't already find it, we could just look it up in the table, and that would give us this solution over here. All right, cool. So your turn. Why don't you find the requested probabilities for parts C and D, And also draw your curves and shade the appropriate region. I find that really helpful, and I do that for every example that I do. So why don't you pause the video and give that a try, and then when you press play again, I'll go through my answer to see if ours match up. Alright, so to draw the curve, I always start with a horizontal line. I draw some bell-shaped looking thing. Okay, don't be jealous if yours don't look as beautiful as mine. Don't worry, just keep practicing and eventually they will be. So I always put my mean of 0 here at the middle. And now we gotta label this z-score, negative 1.23. So that's off here to the left somewhere. Alright, negative 1.23. Cool. And we're trying to find the probability of z being less than or equal to that probability. So we want to this is a disaster. There we go. We want to chop it off here and then shade everything to the left. Okay, cool. And then once you do that, you know you just need to look up this value in the table in the back of the book. So let's go check it out. We're in the negative z-scores here, so we want to go to our negative sheet, which is right here. And what was that z-score we were just working with? I forget. Negative 1.23. So negative 1.23, we got negative 1.2 here. We're going to go over 0, 1, 2, 3. So the answer for this one would be 0.1093. So equals 0.1093. Cool. Awesome. All right, let's try example D. Find the probability that z is greater than negative 1.23. All right, well, I could draw another picture. Not the most straight y-axis, but whatever, we'll deal with it. And we got z equals negative 1.23 here. And we're trying to find the probability that z is greater than that region now. Okay, so the way we find probability of z being greater anything is we need to do 1 minus the probability of z being less than it. So 1 minus the probability of z being less than 1.23. So we could go ahead and look that value up in our back of our textbook, but we already found that in the previous example, so we'll just use that. So it's 1 minus 0.1093. And you punch that baby in your calculator, and what do you get? I don't know off the top of my head. It's probably 0.897. No. 8 point. Oops. That's not right. It'd be 0.8907. That's better. Okay. Cool. There you go. So that's the final answer. Awesome. All right, and the last thing, or not the last thing actually, another thing we'll look at is how to find the area between two z-scores. So the probability that a z-score lies between two values, two z-scores, like in this example 2, part A, find the probability that z is between negative 1.23 and 2.55. The way you do it is you look up the probability for z being less than 2.55 in the table, and then you look up the probability about z being less than negative 1.23 in the table, and then you just subtract those two numbers right there. And once you do that, you'll get your final result. Okay? The intuition here that I like to say is, if you look at a number line, and you want to, let's say I asked you, I don't know, actually, let's say I have these 2 points here. Let's say I'm going to call this 0, I'll call this 4, and I'll call this 6. Okay. We all know how many spaces between 4 and 6. We know that's a distance of 2. But if you didn't know, one way you could find out is you could say, well, what's this distance right here? That distance is 6. And what distance is right here, which is 4. And the way you find the distance in the middle is you subtract 6 minus 4, which is 2. And that's what we're trying to do here. We're trying to find the area in the middle, which you really just find by finding the bigger piece and then subtracting off the smaller piece when they overlap like that. Okay, cool. So your turn. Find the probability that z is between 0.58 and 1.77. So why don't you pause the video, try that, and then when you press play, I'll go through my answer and we'll see if ours matched up. Okay, so first we're going to start by drawing a curve. Very nice looking curve there. And we're going to mark all of our important things. So I always mark 0. Then I'm going to mark z equals 0.58. And this does not have to be very accurate. You're just trying to gain some sense. Really, what's most important is just that you're on the right side of 0. So here's 0.58. Here's 1.77. Cool. And we're trying to find the area in between them. So we're trying to find the area of this region right here. So what we're going to do is we're going to find the probability of z being less than 1.77. Right? Find out what that is. Then we'll find the probability that z is less than 0.58. And then we'll subtract those two values. You cannot just subtract 1.77 from 0.58 and then find that one value in the table. That will not work. Okay? So let's go ahead and find these two values. For 1.77, the value is going to be 1.77 is 9616. So 0.9616. And then for 0.58, you get 0.7190. 7190. 0.7190. And then you just subtract these and find out what you get. I gotta grab my calculator for this one. So let's see. 0.9616 minus 0.7190 is 0.2426. Cool. And so that's your final answer. That's the probability of some z-score being between 0.58 and 1.77. Another little tip I'd like to let you guys in on is I do not recommend you marking up and drawing all over your z-tables the way I have. I can just not save it when I'm done with all of this. But if you write all over your tables, it's going to make it very difficult to be able to read this later in the semester after you've done your 100th or so example in this table. We're going to be referring to this table quite a bit this semester. So again, try not to mark it up too much, or if you do, maybe use pencil. That way you can erase it. If you've already marked it up, it's not a big deal. You can always just print out new copies of it. Okay, so the last thing I want to talk about is finding z-scores when you're given the probability. So working our way backwards. So find the z-score which marks the 90th percentile. So the z-score which delineates the lower 90% from the upper 10% of all z-scores. All right, so we're given this 0.90 in here, right, which is like the inside, our probability, or our area, okay? Now, formally, when we looked at our table, let's go back to our table, so that 0.90 is actually something inside here, right? It's not one of our z-scores, it's actually one of these numbers inside here. So what we basically have to do is we have to go fishing for it, all right? So we have 0.90. What I like to do, a little tip, is I like to rewrite these as 4 decimal places. So rewrite this as 0.9000. because that's what all of the values in the table are. They all have 4 decimal places. So let's go ahead and go fishing for that 0.9000. We know since it's greater than 0.5, we know it's going to be in the positive z-scores, and you can think about that on your own if you'd like. So we're going to go fishing through this table, which I've scribbled all over, for this 0.9000. Where the heck is it? Oh, there's a 0.9032. This is a little bigger, so let's go backwards. 0.9015, 0.8997. All right, so we have 2 values here, which are both pretty close. 0.9000 is not exactly found in my table. So these are my 2 closest ones. So which one of these 2 values is closer to 0.9000? Think about that for a minute. So it's this one right here. It's the 0.8997, right? Because that one's off by only 0.0003, and the other one's off by 0.0015. So the so we go backwards. We got 1.2 and 0.8. So the answer for this one is going to be z equals 1.28. So the answer for this is in fact 1.28. And I like to denote that with a z equals 1.28 like the textbook does right here. Okay, so your turn. Find the z-score which marks the 25th percentile. So the z-score which delineates the lower 25% from the upper 75%. So go ahead, press pause, give this example a try, and then when you press play, I'll work my way through it. Alright, great. So here's my start to draw my curve. I do this for every problem. I strongly recommend that you do too. Don't try to just, wing these. Alright, what we're looking for is the lower 25% from the upper 75%. So first of all, is that going to be to the left of 0 or to the right of 0? Well, it's going to be to the left of 0 because 0 would separate 50% of my data. So I'm looking for my lower 25%. That's definitely going to be to the left of 0. So I know that inside here, my probability is going to equal 0.25. And like I said, I like to write these with 4 decimal places. 0.2500. And what I'm looking for is this z-score right here. I'm looking for what this z-score is. So I got to go fishing. I got to go fishing through my table. I'm going to go to my negative z-score table because I know since my z-score is to the left of 0, it's going to be negative. So I'm going to go to page 288. I'm going to go fishing for that 0.2500 number. So I got my 0.2s down here. I got 0.2420, 2451, 2483, 2514. So it's somewhere in between here. So I'm going to go with whichever one is closer. So if you take a few seconds, the left number here is off by 0.0014. This number is off by 0.0017, so it's going to be this number right here. So I'm going to go to negative 0.6 and up to 0.07. So my final answer is going to be z equals negative, because I'm in the negative table, 0.67. Cool. And that's the final answer. All right. Awesome. All right. So I'll see you guys in class, and we'll be sure to practice more then. Bye.